To start out, let's straighten out some mathematics about the relation between the uniform expansion of the universe and the observed redshifts. We'll use this repeatedly. Let's straighten it out to begin with. So what's a uniform expansion? What I mean by uniform expansion is that all distances grow by the same factor as a function of time. That means that whatever is at a distance d0 now, we'll denote by d0 the distance now, we'll call the present t equals 0. Then I claim that at time t, an object which is now at distance d0 will be at a distance d of t, which is a common number, a of t, called the scale factor, which is common to the entire universe. So the entire universe is expanding by the same factor, and because we call the present t equals 0, then a of 0 is 1, so that d at t equals 0 is exactly d0. That defines what we mean by d0. If the universe is expanding, then for t bigger than 0, a is bigger than 1. For t is less than 0, a is less than 1, and a is growing. But if a is shrinking, then we can describe a contracting universe just as well. We can describe any behavior of the universe by a suitable choice of this function, a of t. So what does this have to do with redshifts? Well, we're going to imagine that near t equal to 0, so for times not too far from the present. What do you mean not too far? Well, we know that the expansion comes with a built-in time scale. We showed that h0 inverse is a quantity with the units of time, and we called it the Hubble time and figured out that it was approximately, in our universe, 13.7 billion years. So if t is small, on the order of cosmic events, then h0 times t, or t divided by th, is not too large. That means we're not looking too far into the past of the universe when we look at time t. And near that, for suitably small times, positive or negative, close to 0, we're going to assert that the function a has an approximation as a linear function. If you plug in t equals 0, you get a of 0 equals 1. And for t not far from 0, we're approximating a by a linear function. Any reasonable function can be so approximated. And we call h0 the coefficient of that linear term in t. And I'm going to assert that this is the Hubble constant. What does this mean? Well, if a of t is given by this, I plug that into this expression, and I get that d of t, which is a of t times d0, is approximately 1 plus h0t times d0. This is d0 plus h0 d0 times t. Now, this is great. Look, the object at t equals 0 was a distance this from us. A short time later, it is at this distance from us, and the change in the distance is proportional to t. Change in the distance divided by the time elapsed gives us the velocity. So what I'm claiming is that this object here is the speed with which this object is receding from us, and we see that our understanding of h0, or our notation of this coefficient as the Hubble constant, is justified because we just found that the speed with which objects are moving away from us at the present time is h0 times their distance from us at the present time. The uniform expansion by a common scale of the entire universe describes the expansion that Hubble found. Now, this expression that says that a for time near 0 is approximated by this linear function, this is the value of a at 0, but this coefficient of the linear term that says how much does a change when time shifts a little bit away from 0, well, this is the rate at which a changes. For example, if a was your position, the change in a per unit time would be your velocity. The notation for this, rate of change of a, is a dot. So a dot above the name of a function of time denotes the rate of change of that. So for example, if the function in question is the position of an object x of t, then x dot of t is the rate at which x changes, and we often write this beautiful equation. The velocity is the rate of change of the position, and it's interesting to convince yourself that the rate of change of the velocity is the acceleration. This is acceleration, that's scale factor. Two different uses of the same letter, as always in physics. So we write this expression, this statement, as the statement that the Hubble constant at the present, at t equals 0, the Hubble constant Hubble measured, is a dot, the rate of change of this function a, at t equals 0. Now, What does this have to do with redshifts? We found that the recessional velocity obeys the Hubble law. We're talking about not Doppler redshifts, we said, but cosmological redshifts in the context of cosmology. We assert that as the universe expands, and this is a result of general relativity, that we're going to steal, and later quote, we're not going to derive it anyway, but it's a result from general relativity that as the universe expands, the wavelengths of light expand at the same time. We'll discuss that when we get to a relativistic version of cosmology. But what that means is that the redshift, which we defined as z, such that 1 plus z is the ratio of the observed wavelength to the wavelength at which some light was emitted. Well, if wavelengths stretch like everything else, then the ratio of the wavelength now, or at observation, to the wavelength at emission, is the ratio of all other distances at observation to their length at emission. And since we are observing now, we can use the fact that t observation is equal to 0. We are now living in the present, and a of 0 is 1, to get this relation between the function a and the redshift we observe for distant wavelengths. And now what we're going to do is insert this approximation for the value of a into this expression for z. So I'm going to keep going here. Notice that this time, t emission, is always in the past. We can't observe the future. So t emission is always a number less than 0. This is a negative number. If a is a growing function and it's 1 now, then a of t emission is less than 1. Its inverse is a number bigger than 1, and we observe a positive redshift. And now let me compute our approximation to this redshift. So this is approximately the same as 1 plus over, I'm going to insert here, 1 plus h0 times t emission. That's our linear approximation to a inserted into the definition of the redshift. And now this is right for Newton's approximation. This is 1 plus h0 t emission, quantity to the negative 1. h0t, by our assumption, is much smaller than 1, so this is approximately the same as 1 minus h0 t emission. This is the Newton approximation to this expression, so let's write that out cleanly. Notice that t emission is negative, so this is a number larger than 1. We have a positive redshift. Life is good. There's that written cleanly. And now, of course, identifying this is equal to that, I can cancel the 1's, and I find an expression for z. The redshift is minus h0 times t emission. Remember that since t emission is always negative, this is a positive number. We never see blue shifts because we're always looking into the past. Now, this gives us a statement that the redshift of observed object is linear in the time at which the light was emitted. Hubble discovered a linear relation between redshift and distance. So how far are these objects that we're observing? And this is a tricky question. If we observe an object now, and the light was emitted from that object at time 1 billion years ago, how far is the object? Well, remember, the object is moving. This is confusing. It's easiest to think about this from the point of view of the object. How far are we now from an object which emitted light 1 billion years ago that we are now observing? Well, that's an easy answer. If the object emitted the light 1 billion years ago, the light is now 1 billion light years away from that object because light moves at speed c. And so the distance between us and the object at this present time is just c times the time the light had to transit, and the time of transit is negative t emission. Remember, because t is a negative number, this is the difference between present time and time of emission. So this is the distance. Looking at our expression for z and our expression for d0, we can rewrite z as equal to h0 d0 divided by c, which was Hubble's original relation, that the redshift was h0 over c times the observed distance. And so we have reproduced in this context the meaning of Hubble's constant in the context of a cosmological expansion with a scale factor given by a function of t, a of t. h0, the present Hubble constant, is the rate of change of a at the present time when a is given by the value 1. Great. One more question. Suppose that we lived 3 billion years in the future. What would the Hubble constant be that we measure then? Well, that, of course, depends on the nature of the evolution of the universe, but A of t gives us the nature of the evolution of the universe. So if we know the function A of t, we can answer this question. How do we do that? Well, we project ourselves into the future, or alternatively into the past, and pick a time, t star, and we're going to discuss the experience of observers living at t star. They do the same thing that we do. They approximate the scale factor, except they approximate it not near 0, where a of 0 is 1, but near t star, where a of t star is whatever it is at their epoch. And again, they call the rate of change of a at time t star the coefficient of the linear term that describes as t differs from t star, how does a change. So this again is the rate of change of a at the time t star. Now, they plug this same idea into their expression. So they would say that for t time near their time, d of t, which is a of t times d0, is approximately equal to a of t star plus a dot, rate of change at t star, times t minus t star, all this times d0. Now, this we can expand. This times that is a of t star times d0. And the other thing is a dot of t star times d0 times t minus t star. Well, the first term is great. A of t dot star times d0 is by definition d of t star. That's great. If we set t equal t star, this disappears. We find that at t star, the object is where it started. How far has it moved? Well, as we expected, we find the time elapsed since t star times some number. And so this number, we therefore conclude, is the speed with which the object is moving, or the velocity, the recessional velocity, v, at time t star times t minus t star. And so what this tells us is that v at time t star is just a dot of t star times d0. Now, that's very nice, but we didn't want to write, this gives us a linear relation between the speed at t star and the distance now. But we didn't want the relation between the speed at t star and the distance now, because the distances they measure will be these distances, d of t star. So how do we rewrite this in terms of the distance they measure? Well, remember that d of t star is equal to a of t star times d0, or d0 is d of any time, in particular t star, divided by a of t star. So plugging that into here, we find that the recessional velocity at time t star is given by a dot of t star times d0 divided by a of t star. Oh, look, now times d of t star. And now we have what we wanted. We have the recessional velocity at time t star given by something times the distance at time t star. We identify this object as the Hubble constant that they would have measured for the reasons we just specified if they made measurements of the Hubble constant at their time. So here's that whole calculation spread out. And again, we're going to identify the coefficient of d of t minus t star as the velocity, and the coefficient of d in the velocity as the Hubble constant at time t star. And so the Hubble constant at any time is not a constant. Depending on the nature of the function a, at any time you would measure a changing Hubble constant. But it would be constant in the sense that it would be velocities would be proportional to distances, at least for distances that are not too large, so t emission is not too far into the past. Now, we can ask, what does it mean for h to be constant? We'll talk about that later. We note that it does not mean strictly setting this equal. So if a is in fact a linear function, what does that mean? That means that this is an exact equality. The rate of change of a is then constant. A dot is a constant number. But if you look at the Hubble constant, this will be, the numerator will be constant, but as t grows, a will be growing. So the denominator is growing. An expansion that is in which the scale factor is linear in time corresponds to a decreasing Hubble constant. That is not the meaning of Hubble constant not changing with time. We'll see later what kind of expansion has a constant Hubble constant.